When talking about quantum materials, of course, this is now a very popular term, and people use this loosely to describe different kinds of materials. As you might have heard, quantum materials from the aspects of like low-dimensional systems, such as let's say quantum Hall systems, to the heterostructure, complex magnetic structures such as fermions, as well as even the conventional condensed matter. Um, the systems that we have studied extensively for last decade, like superconductors, as well as new fields which are emerging in recent years, such as mooded physics in low-dimensional systems. For my topic, research topic, I mainly focus on these topological materials. So I'll try to first introduce this topic and these materials and try to share with you what are the interesting aspects of these systems and how we can find these new topological materials using structural symmetry arguments. Whereas those arguments I will try to expand to also find other types of quantum materials as well, which will be interesting for low dimensional device fabrication as well. So to introduce the topological materials, we should start from the band theory of solids. So if you have, I'm guessing that most of us are familiar with the band theory of solids in condensed matter. If you look at the origin of band theory of solids, we should go to the energy state of an atom. Basically, quantum mechanics. We have studied how the energy states in an individual atom, electrons in an individual atom should look like. So they are these discrete levels, and we describe this at different orbitals like 1s, 2s, 2p, and at different energy values. Now, in crystalline solid, of course, instead of we have one atom, we have Avogadro number of atoms. So in that case, you cannot, the energy state is not discrete anymore. And if you want to find what is the energy state in crystalline solid, which we will try to use a quantum mechanical model. So we will we try to solve the Schrodinger equation under periodic potential, because in a lattice you have a period. We assume that the potential is periodic in nature, with having periodicity same as the lattice periodicity. So if you try to solve this Schrodinger equation in periodic potential using the simplified models such as Kronig-Penney model, what we end up with is that energy we have instead of these discrete levels in an individual atom, we have energy bands. So you have the main two bands which we are mainly concerned with in a material for electronic properties at least are conduction and valence band. And depending on whether this conduction and valence band are touching each other or having some kind of energy gap between them, we classify different materials in terms in the bucket of metals, insulators, or semiconductors, depending on whether you have a finite band gap or not, and what is the value of this band gap. Now, this is a simplified picture, but we know that in a real material, the bands doesn't look like this kind of flat at all. So if you look at the band structure of a normal metal like copper, you'll see these bands are really complex. So you have lots of curvature in the bands and lots of bands crossing each other. So it's very messy in nature. So also, another interesting thing is that we see, if you remember, the normal, a simple model of particle in a box in quantum mechanics, we know that the energy in the box is quantized, and that energy or the quantized energy follows a dispersion relation of E proportional to k square. In a periodic potential in conic periodal, you can think this as a basically a periodic potential is nothing but a collection of these quantum wells at the lattice points, and the overall energy state still gives you the energy value still gives you this quadratic dispersion relation. So this is the main thing to keep in mind. If you want to introduce the topological band theory, so you want to, we are trying to introduce the idea of topology into this band theory, our conventional idea of band theory. We should start with this simplified picture. I think this is quite popular now. You might have encountered this picture several times in different talks and articles. So to give you one just simplified picture, the idea of topology is purely mathematical in nature. You can think of this as an idea of how to distinguish between different geometrical objects. And in topology, the idea of topology is that you classify different geometrical objects in different classes depending on some kind of parameter, which we call topological invariant. And you can actually you can go from one class of this material, one class of this object to next class if you only when you discontinuously change this topological invariant. So, for example, if you have a solid sphere and if you somehow can, let's say, deform it in a way that you continuously deform it, don't introduce any discontinuity, that is, you cannot cut the object or you cannot glue to something else, then you remain in the same topological class. But somehow, if you introduce some kind of discontinuity, for example, here you introduce a hole in the that sphere, you actually change the topological invariant. In this case, let's say the number of holes is the topological invariant from 0 to 1, and you then go to a new topological class. So by then, you can here from these objects, you can see that these first four objects are in a particular topological class, whereas this next four object in the second topological class, and this last one is a new topological class. So you have here only three topological classes, although they look geometric like from when you are looking at them, although they look different, these first four objects, they topologically speaking, they are in the same topological class, and so far and so on. So how can we translate this idea of topology into band theory? So think about an insulator, a trivial insulator. So we have a conduction and valence band, and let's say the Fermi energy is lying somewhere between this conduction and valence band. So this is a typical insulator from the band theory. Now let's say you have the ability of somehow tuning the band gap. Let's say you can tune the Hamiltonian in such a way that you can tune the band gap. So now if you can correlate with topology, as long as you could change the band gap, but as long as you don't touch this bands, that is that band gap remains finite, you remain in a particular topological class. But as soon as you touch these two bands, then we go to a new topological class. And if we somehow go even further and we have a band inversion between conduction and valence band, sorry. Okay. So if you have some kind of band inversion, so you create an insulator in the system, but here, because of this inverted band gap, you actually pass through from a finite to zero band gap to inverted band gap. You create an insulator which is a distinct topological in a distinct topological class. So that's how the idea of topological insulators are born. Apart from this band inversion, you also have some gapless bands in this within this band gap, and this comes from the surface of the physical boundary of the material, and these are called surface states. So this idea, if you want to understand the idea of surface state, you can think this similar to a quantum Hall effect system, where you have you have the cyclotron orbits in the interior of this material, whereas the boundary you have something called chiral edge state, where what is called chiral because the electrons can only move into one direction, and this only appears at the physical boundary of the system. So this surface state of topology insulator is similar to this edge states of quantum Hall effect, but the major difference here there is that to generate quantum Hall effect, you need an external magnetic field, where in topological insulator to generate the surface state as well as band inversion, you don't need any external magnetic field. Instead, you need some internal parameter, and the most important internal parameter for this material is the spin orbit coupling. So if you have a strong spin orbit coupling of electron spin and electron orbital motion, you can create this kind of state. For my work, I am more focused on this middle part where you have this just conduction and valence for band touching at a certain point, and you create something called topological semi-metal. So if you look at the topological semi-metal, now as I introduced, there is in topology insulator, you have interesting surface state. Similar to topology insulator, in topology semi-metals, you also have two distinct state. One is in the bulk state, which is in the interior of a material, whereas the surface state that has a physical boundary, you have some interesting surface states going on. So let us first discuss what is happening in the bulk material. So the bulk you have basically a crossing between conduction and valence band, and this kind of crossing usually, if you have read some chemistry, you know that usually band crossing in materials, they usually often undergoes hybridization, band hybridization, and usually you open up gaps. But in this topological semi-metal, what happened? Although we open up gap at most of the points, at certain points in the momentum space, we have some gapless band. So this band gap remains becomes zero at some certain points. Now, this band gap, the why at this point the band store cannot hybridize and remains gapless is actually can be argued from the symmetry point of view. So crystallographic symmetry play a crucial role in protecting this kind of gapless states. So usually in topology of same metals, usually it is some kind of mirror or rotational symmetry in the crystal. So if you have some kind of rotational symmetry, that somehow can actually protect this kind of band crossing. The second interesting thing is that near these crossing points, the band shows a linear dispersion relation. What my linear dispersion relation? That is, the energy is proportional to momentum instead of the momentum square as we have seen for this band theory, the copper I discussed, right? So if you are also because these bands are spin degenerate, that means each band also consists of both spin up and spin down states of electron. So these crossing points are basically fourfold degenerate. So you have a fourfold degenerate crossing points, and near this crossing point, you have a linear dispersion relation. So if you want to describe what is the how the motion of the electrons, what will be equation of motion for the electrons, you want to use the quantum mechanical models. Now you know that the normal quadratic dispersion relation, Schrodinger equation periodic potential, which gives quadratic dispersion relation, will not hold here because of the linear dispersion. So then you have to use something called relativistic quantum mechanics. If you are familiar with relativistic quantum mechanics, you might have encountered something called Dirac Hamiltonian, where you have this kind of the form of Hamiltonian, where sigma is the wave vector, spin vector. So it contains the Pauli spin matrices. So this is basically fourfold because these are matrices, right? So it's a fourfold. This can describe a fourfold degenerate crossings, whereas this kind of quantum mechanical model gives you linear dispersion relation. So that means if only thing is different here with the normal Dirac Hamiltonian that we read is that here you instead of this Vf we usually have c, which is velocity of light in that quantum mechanics in the model. So why we have put Vf here? Vf is basically the Fermi velocity because in a real material electrons cannot move beyond the limit of Fermi velocity. So although we replace the C with Vf, all the other properties of this Hamiltonian remain same as quantum mechanics, relativistic quantum mechanics, and all the relativistic phenomena predicted by like proposed from this model, from a relativistic quantum mechanical model, should also hold here. So this is why we call this kind of semi-metals as topological Dirac semi-metals, because you can study relativistic Dirac physics while remaining in the low energy scale of a condensed matter system. If you somehow can leave the spin degeneracy in the system by breaking, let's say, time reversal symmetry, what you can do is that you can split each of these crossings because each band is spin degenerate, spin up and down. So if you somehow break the spin degeneracy, each of these reactions will break into two points, um, depending on because of point will have a particular chirality also. So in that case, you have to use something called wild semi-metal, wild Hamiltonian, where you introduce the idea of chirality. So basically, Dirac point is a combination of two wild points, and if you break the time reversal symmetry, you break one four-fold degenerate Dirac point to a pair of two-fold degenerate wild points. Secondly, the surface state is also interesting because if you have a Dirac semi-metal, the surface state is shows something called spin polarized Fermi arc, where this kind of 2D Fermi arc state actually connects the projection of this Dirac point to the surface. Whereas in wild semi-metal case, you have something called broken Fermi arc. So in Dirac semi-metal, you have this complete Fermi arc spin up one direction, spin down another direction. In wild semi-metal, you have broken, that is half of this will be on top surface, while the other half will be on the opposite surface. So both this bulk state and surface states are very interesting. They are symmetry protected, showing relativistic phenomena. So if you want to study this kind of relativistic phenomena, it's a good these materials and give you the opportunity to study them in a very cost-effective way in tabletop experiments in a lab. Apart from this interesting fundamental physics, because of these unusual properties of this material, there are also a lot of application proposals. For example, because of the surface states of these topological insulators have been shown to be very robust against impurities, and they are chiral in nature, and they don't support backscattering. There are proposal of using is that for low power electronics, because effectively you can have almost dissipation-less current at the surface of the topological insulators. So there are proposal of these low-powered electronic devices using topological insulators. Then there are also, if you might have heard about quantum computation nowadays, is very popular. So to design the qubit, one proposal is that if you can find topological superconductivity, there's possibility of realizing Majorana fermions, which can be used for designing the qubits in quantum computation. Then also there are topological spintronic devices applications which are proposed. So all these things made it so interesting and so popular that if you want to now find whether some material has some topological property, has something interesting topological property or not, you can go to this topological material databases. So this topological material database, there are two main ones. So this is the one which is jointly maintained by Max Planck Dresden and Max Planck Institute Dresden and Princeton University, where what they did is that they used all the reported structural parameters for known compounds from the material databases, ran a simulation, basically density functional theory based calculations, calculate the band structure, calculate the topological invariant of this material, and try to see they identify which material has some topological band state or has some topological state or not. So this is very easy to use. You can go and select different elements, combination of different elements, and it will give you the list of compounds. And then it will also show the band structure. And then let's say, for example, a popular example is cadmium arsenide, which is the first discovered topological Dirac semi-metal. You can go there and it will actually show the structure, band structure. Also, will give you all the parameters, topology invariant, and will tell you whether something has some interesting topological property or not. So it's very user friendly. Now we realize that there is actually a very basic fundamental flaw of using this kind of databases blindly. For example, if you see this material called strontium zinc bismuth 2, if you see the band structure reported in the database, it shows this, which is very messy in nature, and we don't see any interesting linear band structure, like nice linear bands near the Fermi energy and whatever. It cannot actually comment on that. It's very messy in nature. But if you actually look at the structural parameters and do your band structure calculation on your own and keep in mind all the spin orbit coupling, all the things appropriately, you actually end up with a band structure which is much more interesting. So you have this nice linear bands crossing at the Fermi level with linear dispersion relation at large energy range. So also here, so it's very clean topological semi metal, which you cannot find from this database. So it's not always advisable to follow this material database, this kind of topological database blindly. Instead of try to find some structural symmetry arguments or clues which might give you whether some material can have some interesting topological property or not. So for that, we focus on something called structural motifs. So when we call structural motif, we mean basically a group of atoms in a structure, which is basically repeating itself in the whole structure. So for example, here you can, in this kind of crystal structure, you can find a motif, something like this hexagonal motif, and you can actually see that throughout the structure, this hexagonal motif is basically repeating itself. It can also find different motifs in the same crystal structure. For example, here, two different kinds of motifs are shown, right? But the same motif you can repeat throughout the structure and you can generate the whole structure. So it comes from the symmetry argument. So now the question is, can we try to construct the band structure of a material only looking at the structural motif of of a compound? So this idea was put really nicely forward by Professor Roald Hoffman and Cornell in 1987. So this is a very interesting paper if you want to read. So what he did is that it's a chemist point of view. He is a Nobel laureate chemist who introduced the idea of let's say it's a simple model of 1D chain of hydrogen atoms, and he was trying to he proposed from a chemist point of view, only looking at the orbitals, how can you actually construct a band structure only looking at the bonding and anti-bonding between different orbitals between these two different atoms in this chain. Now, for his model, there is also a problem with 1D chain. We know that the 1D chains are very unstable in nature. I'll maybe show you in the next slide also. In nature, because they often undergo this kind of dimerization, because two atoms, consecutive atoms, come closer together, they form a stronger bond, and you create something called. So instead of a nice chain of atoms, you have this kind of distorted chain. So this spiral distortion is also has been observed to open band gaps. So that will I'll discuss in a minute. So if you can, if you want to use this idea to, let's say, draw the band structure of other like more complex motif, we'll discuss the idea of graphene, which is a very famous example of this 2D material, and people have shown this as a nice linear bands in this material with this kind of Dirac cones in the band structure. So this was actually formed by this paper. This review paper is from my postdoc supervisor, Professor Leslie Shoup, who came up with this kind of brilliant idea is to generalize this idea of this 1D chain, how to construct a band structure to graphene. So in graphene, you have basically 2D shades of carbon atoms. So they form this hexagonal pattern. So if you know that carbon atoms, they have 4 electrons at the outer shell. So if you see that three of these electrons form this sp2 hybridized bonds with the neighboring carbon atom, whereas the fourth atom reside in the pz orbital. So if you want to construct the band structure from using that, from the idea that Professor Roald Hoffman proposed, is that you draw something called something like this, where you have only one PZ band which is half filled, or the other bands are fully filled and they are not contributing at the Fermi energy. So if you look at the band structure, it looks nothing like what we have in graphene actually. So that means this is incomplete in nature, this band structure like this. So, but the idea is that if you also need to think about the number of electrons per unit cell in a material. So for graphene, although it's a hexagonal symmetry, if you look at the unit cell of this material, that unit cell looks something like this. So in this unit cell, instead of one carbon atom in graphene, you have actually two carbon atoms. Now you see this kind of lattice is in real space, but when we are drawing the band structure, we drawing in momentum space, right? So inverse. So if your unit cell has two atoms, so basically it's a doubling in size, the momentum space should be halved in size. So if you do that, we do something called band folding. So you fold this band on like with respect to this midpoint, and you get something like this. So you get a crossing point. So if you extend this whole band structure to the second prevalent zone, what you end up with basically crossing between this fuzzy band, which looks very similar what we have from a actually calculation of the band structure of in graphene. So now I have already mentioned that usually in 1D chains you have this pulse distortion which distort and actually opens a band gap. In graphene that should be also the case, but here what happens is that the extra lone pair of electron in the PZ orbital, they got delocalized throughout this graphene sheet, and they help to create a second pi bond between neighboring carbon atoms. So this delocalized electron throughout the graphene sheet actually stabilize this band crossing, and you get this dispersion, nicely dispersive, gapless crossing in the band structure. So if you look at the just quickly to tell you the pulse distortion, what happens in the in pulse distortion? You have if you have a 1D chain of atoms like this in pulse distortion, these atoms, neighboring atoms, form dimers. Basically, they come closer together, form a stronger bonds, and double the unit cell in size because the lattice periodicity basically is doubling from A to 2A, and this usually opens up band gaps in the brilliant zone in this kind of gaps in the band structure. And they also introduce something called charge density. So what happens is that in a normal 1D chain, we expect if it's a metal, if you have free electrons and the free electron should be uniform, the density of electrons should be uniform throughout the chain. But if you have this kind of dimerization, the electron density throughout the chain doesn't stay uniform. So instead, this also shows a periodicity of 2A. So you create a density, a wave of the density of electrons, and this is called charge density. So this idea of pulse distortion charge density will be actually important for our the later slides. So for us, we wanted to talk about topological materials, right? So let me introduce now the main family that I'm interested in. This is called a square net material. So the first example in this family and the most famous example is a material called ZRSI. So zirconium, silicon, sulfur. If you look at the crystal structure, and this has three. You have this 2D layers of silicon atoms, and between these two layers of silicon atoms, you have sandwiched the zirconium and sulfur atoms in a way they form a cage type structure. Now, this particular 2D layer of silicon atoms is actually the most interesting part in this material that I will show in the next slide, next slide. But if you look at the band structure, the band structure looks very clean. So if you have really nice linear dispersive bands near the Fermi energy without any interference from any other non-interesting bands. So this is actually this is the theoretical calculation, and which was so we then there is another technique called angle of potential spectroscopy, which I have give you the ability to directly visualize the band structure in a material using protoelectron spectroscopy. So by doing that, we actually can confirm that this material indeed has this kind of nice linear dispersive bands in this material, which is very uncommon in most of the systems because they also show a lot of other bands interfering with them nearby, and it becomes the band structure looks very messy. So this material shows very clean bands, linear bands, and very clean topological properties. Just to spend few minutes to discuss why this linear bands at the Fermi energy is important, because this nice linear bands at the Fermi energy without interference from other bands actually give you really interesting electronic transport properties. For example, we see really large magnetic resistance in the material. So the magnetic resistance, sorry, can I? Yeah, so large magnetic resistance in the material. Also, apart from the matter resistance, we also see these oscillatory patterns, which we can actually subtract by subtracting a background. We can actually separate from the raw data, and we see this nice oscillatory pattern in the system. Now, these oscillations are called Subnikov-Dehaz oscillation or quantum oscillation in general. So, why these are interesting? Because quantum oscillation comes from something called Landau quantization in the system. So what you have basically, you have electrons in the material. If you apply a magnetic field, if you have a strong enough magnetic field, what you do is that you create cyclotron motion of the electron. Now, if without any magnetic field, when the electrons are moving freely, the energy states of the electrons remains continuous. They can have any value. But when you create this cyclotron motion, the electrons, if you use the quantum mechanical model, instead of this continuous energy states, you create a discrete energy states and discrete levels, and this got called Landau levels, and these have similar energy as a simple harmonic oscillator, where the lowest Landau level has energy of half h cut omega c, or omega c the cyclotron frequency, or like the energy range in energy state. Two consecutive energy states are separated by energy difference of h cut omega c. Now, the degeneracy of this energy states are actually proportional to B, and if you increase the magnetic field strength, what you do is that you increase the degeneracy of the electron of this Landau levels, and more electrons come actually try to populate lowest Landau level to minimize the energy from the, so they come from highest to lower Landau level. So by doing that, what you do that with continuous magnetic field increase, you also emptying higher Landau levels, and that kind of emptying of consecutive Landau levels gives you this oscillatory patterns in the matter resistance. Now, the oscillation is very interesting because this also gives us an excellent tool to study the Fermi surface property of the material. So it has been shown that this oscillation frequency F is actually proportional to the Fermi surface cross section perpendicular to the applied magnetic field direction. Actually, this is called optimal Fermi surface cross section perpendicular magnetic field. So either maximum or minimum. So something like this, if you have a Fermi surface like this, so if you rotate the magnetic field along different direction, you should be in principle able to get Fermi surface cross section along different direction. And by doing that, you can construct a full Fermi surface of a material by measuring quantum oscillation along different direction. So this is a very powerful tool, and by doing that, we showed that this material, this ZRSIS material, has a quasi two-dimensional Fermi surface. That is, the cross section becomes from high from surface cross section along one direction to becomes almost negligible cross section along the perpendicular direction, mutually perpendicular direction. So basically, you go from the Fermi surface looks something like almost like a quasi two-dimensional sheet. So that kind of like anisotropic Fermi surface can also give you very anisotropic matter resistance along two different directions. Anyway, so if you look at the, so if you want to see why this material, particularly this material, has this kind of nice topological bands in the crystals, in the topological state in the band structure, so then we should look at the something interesting happening in the crystal structure, and which is at that 2D layer of this silicon atoms. So if you look at that layer in a different view, you get something like this. So these atoms form a particular motif in the crystal structure, which is called a square net motif, square net structure. So if you do a tight binding model, which is basically same as what we had did for graphene, but because you have a complex structure, so instead of doing by hand, you can just do a tight binding model. The idea remains same. You create the band structure, which is qualitatively similar to what we did for density functional theory. If you compare with the density functional theory, so you see we have this nice linear bands and the Fermi energy, as well as we have two other bands, band crossing below and above the Fermi energy, which are called non-symmetric Dirac crossing, because these are protected by non-symmetric symmetry, which I am not going in detail, but here you can also see them here and here, these two bands, which will be interesting, but I'm not going into details. So anyways, so that means this 2D this coordinate motif is the most interesting part, and it can generate all the interesting features that we are actually looking for in a topological material. So this idea was actually not very new, to be honest, because in 2015, Young and Ken, Charles Ken, who is a very famous theory of conditional physicist and did lots of early prediction of this topological material. They actually showed that in a 2D square lattice, there is a possibility of creating a non-symmetric Dirac-Metal state. So the idea was still there, but in this kind of 2D motif, we can actually see that in a 3D crystal structure can generate all the interesting bands in a material. So that means if you can find this nicely 2D motif in a crystal structure, then our job should be done because we should have the nice topological value in the crystal in the system. But turns out this is not that simple. So most of the time, this squareness structure actually undergoes different kind of bias distortion, and rarely they remain in this undistorted form. So our job becomes even more difficult. So we might now need to find what is the conditions which should ensure that a crystal motif remains this 2D corner structure motif remains undistorted in a material. To do that, we can find actually two factors which are contributing here. So if you, so my colleague Sebastian, Dr. Sebastian Clemens did a database search and tried to find some correlation between all the square net material in the database possible, and try to find which one has this undistorted square net motif in the crystal structure. So he came up with two conditions. One is a tolerance factor, which is basically the bond, basically ratio between bond distances between atoms within the square net and also between the square net and next layer. So basically, the idea is that the square net should be properly isolated from the other layer so that they don't have form any the atoms in the square net don't form doesn't form any bond with the neighboring atoms in the other layer. But most interesting thingly is that they we found that there is a particular condition which is called electron count, and it is basically the what is the number of electrons per atom at the square net side. And if you have magic number of 6, only then the square net remains gapless, undistorted. Otherwise, they create different kind of distortion. So what happens is that this is something similar to graphene that we discussed. In the case of a 6 electron per square net atom in the crystal, what happens is that the electrons become delocalized throughout the square net, and they form something called hypervalent bond. So these hypervalent bonds can also only be uh, formed by these localized electrons. And this hypervalent bonds ensure that your square net remains undistorted. Otherwise, if you go below 6 or above 6 in a 2D square net motif, you distort the square net. Now, I should mention that the 6 electron per atom is only magic number for only for 2D motif, whereas if you go to 1D and or 3D, as a matter of fact, the magic number will change. But for 2D motif in a crystal structure, the 6 is the magic number here. So we thought, okay, well, it's well and good, but can we use this kind of distortion in the square net to some our advantage? So we can use this as a control parameter to can control the topological property or other physical property in a material. To do that, we selected a particular subgroup of the square net family called the lanthanide, basically lanthanide antimony telluride. And in this system, you see the crystal structure has similar to the zirconium silicon sulfur. Only difference here is that instead of silicon square net, you have the antimony square net. And because you have a lanthanide, there is also possibility of inducing magnetism in the system because lanthanides usually give you magnetism for electrons mostly. So if you look at the band structure of this rare earth antimony tellurides, they have similar band structure of ZRSIS. So band structure wise they remain same, but antimony square net should give us a higher controllability. How? To show that, we particularly selected a metal. A particular example in this family is cerium antimony telluride, which is also topological same metal, which has linear bands near the Fermi energy and is an antiferromagnetic nature with a small magnetic field. You can actually polarize the system to a fully spin polarized system at a field of merely zero point 0.2 Tesla. So is an antiferromagnetic ground state. And also from the band structure, it has been shown that this material, depending on the spin arrangement, if you can somehow change the spin arrangement using an external magnetic field, you can also change the degeneracy of these band crossings, and you can have even higher order topological state in the system, let's say 6-fold or 5-fold degenerate band crossing, which is even more interesting. So our idea is to take cerium antimony telluride and try to replace that antimony atoms at the square net from tellurium. Why it's interesting because tellurium and antimony has almost similar ionic radii. only difference being that tellurium has one extra electron at the outer shell. So that means, in principle, if you can somehow do this, we should be putting more electron at the square net side. So we'll be disturbing this balance of 6 electrons per square atom at the square net, and that should give us a distortion at the square net, and as well as this pulse distortion, as well as some introduction of some kind of charge density will be possible. So to confirm that, what we did a single crystal X-ray diffraction. So you would take a single crystal, you shoot X-ray, you collect all the diffraction along different angles, and you construct this kind of precision images. So if you look at this material, almost at the parent compound, on the compound, you see nice this kind of diffraction peaks, and then this, if you solve this crystal structure, is tetragonal in nature, is almost same as current compounds. So there is nothing interesting there. But as you go put more and more tellurium and in place of antimony at the square net, you see there are some extra peaks appear in the system. So these extra peaks are something called, here is more apparent. You can see these extra peaks. These peaks are called satellite peaks, and there are indication of formation of charge density wave in the system. So you can also solve this diffraction pattern and find the crystal structure itself. And when we did, we see this, we in this start to deform this square net as we put more and more tellurium and the antimony. So this is only the square net pattern we are talking about. So you see different kind of distortion at different doping levels. As I have also mentioned, this distortion also change the periodicity of the lattice itself. Like you have different kind of modulation, instead of, for example, linear chain, the periodicity become double in size. So here also, in kind of complex structure, with this pulse distortion at the square net, we also create higher level, a different level of modulation. For example, you have a 5-fold modulation, 3-fold, and also 3 cos 3 cos 2. That means the unit cell of the material becomes modulated by 3-fold along x and y direction, and 2-fold along z direction. So you modulate the crystal structure itself. Now, if you look at the magnetic properties, this shows interesting magnetic properties, but also something called Devil's staircase. But let's skip this part. Let's focus on the what happened at the electronic band structure, because we are more interested in that. So now, as I mentioned, that okay, let us first think. The first point is that what we are doing basically in the system, we are putting more electron at the square net. So if you look at a crystal band structure and you have a Fermi energy, and if you are putting more and more electron in the system, so in future, what should do? The Fermi energy should move upwards, right? Move in energy, because you are filling more electrons, so filling the bands. So that's the one point. But second thing we also mentioned, this pulse distortion actually opens up band gaps. So if the band gaps are opening, so the some of these bands should also get opened, and some of these bands will vanish at the Fermi energy, right? So if that happens, what will happen with the topological state? So we see that with this material, something very interesting can happen. I remember I mentioned that there is something called non-symmetric Dirac cone, which is much above and below the Fermi energy in the system. So it is possible that as you put more and more electrons in the system, the Fermi energy should go up and reach at a point where the Fermi energy should lie near this non-symmetric Dirac cone point, right? What we observed is that this charge wave, which omits this some of the bands due to pulse distortion, is actually beneficial to our case, because this seems to be selectively opening band gap. What I mean by selectively opening band gap is that it is getting rid of some of the bands, but keeping the only band which remains gapless is this non-symmetric Dirac crossing in this material. So by using charge density wave, what is we basically doing is that using is like an eraser to erase all the non-important bands near the non-symmetric Dirac crossing, and the only interesting crossing remains gapless. So by doing this, the charge density wave actually help us to create an clean non-symmetric Dirac semi-metal, which is very interesting, because you can now, because the Fermi energy is also near this non-symmetric point. In principle, if you measure topological electronic property, you should be able to study the properties of non-symmetric Dirac fermion in the system. So this idea of this proposal of using CDW to clean up the band structure, we also confirm from photoemission spectroscopy, where we see this kind of clean, isolated Dirac cone in the system using charge density. Another interesting aspect happens when you have this complex alternative system with very complex modulation of 3 cos 2. We see this material this at this doping range. It shows it shows a Fermi surface, some linear bands near the Fermi energy. But what is interesting in this particular doping range, that we thought that this material should have very nice metallic properties because of the presence of Fermi surface, as well as high matter, large positive matter resistance. But to our surprise, this material shows semiconducting property with a large colossal negative matter resistance, which is very unusual in nature. And we think that this is something to related with something called quench disorder, when you have this highly doped system, and that can give you to this. But let's skip this part in I'm not discuss in detail. Let's the second part, which is I think will be most interesting to other some of you, because you are interested in low dimensional physics as well. So we use this idea of square net materials and undistorted square net structure to find new interesting topological materials. So the idea is, can we use this idea to generalize to find other kind of quantum
Uh,
materials as well? Yes.
Sorry to interrupt. You
Yeah.
have 10 minutes.
Yeah, I'm trying to wrap up. Yes,
Uh,
quickly. Yes.
okay.
Yeah, so just to give you, so the idea is, can we find other kind of quantum materials? So here we are interested in magnetic 2D van der Waals materials, which can be exfoliated and can be used to create devices, right? So one example is gadolinium tritelluride, which has this tellurium square net. But unlike the undistorted square net, here the square nets are already distorted. We have distorted square net, you have charges to wave. So that means the band structure is not that important from topological point of view. But what is interesting is that material has clearly quite large interlayer distance. And because although the square net is distorted, and it doesn't have topological property, it's still keeping some of the steep bands in the crystal band structure. Now, these usually steep bands give you low effective mass, that means high mobility carriers, and also because of the gadolinium, this material is a possibility of becoming a high mobility low dimensional magnet. It is indeed the case. So this material is an antiferromagnet, which can be exfoliated down to monolayer using scotch tape really easily, and the mobility value is very high. So it is like high mobility magnet. One problem with this material, although, is that this material is very air sensitive. So if you exfoliate this material with thin flakes, they will expose in air within a few minutes, 5 to 6 minutes. It will get oxidized really easily. So we thought that we know that idea, general idea is that, can we use the idea of this already distorted square net with which will give you some steep bands near the Fermi energy and layered compound, we should have a possibility of becoming a van der Waals system, being a van der Waals system. Can we find this kind of using this condition screen through and find new high mobility magnets and possibly air stable. So to do that, you can actually find this kind of van der Waals material database, where there are they will show you these are the only van der Waals material possible from the reported structural data in the material database. But this kind of database is very imperfect, because most of the time density functional theory, which they use to screen through this database, they cannot predict the interlayer distance really accurately. So instead of doing that, we focused on our idea of this structural motif, and what we end up with, finding this material, which have a square net of tantalum, which is undistorted, as well as a distorted square net of cobalt atom. Because of this cobalt, we thought of having this. This should have some magnetism, and it looks fairly layered with so possibly large interlayer distance that we needed to confirm. And this distortion of this coordinate of this cobalt coordinate is very apparent if you look at from other view, where you can see this consecutive cobalt atoms are close by or far from each other, right? So if you look at the TM image of this, so it is HRTM image, you can see these have large interlayer distance, And the van der Waals, the gap in this interlayer distance between this in this material is as large as 0.314 nanometer, which is even larger than graphene and most of the transition metal chalcogenase. So this material can be easily exfoliated, and we obtain this flakes of this like 10 nanometer flakes. When we expose this flake in air for 4 months under optical microscope, we see that it doesn't change at all. So it's very air stable material. We then also went on to actually got monolayer of this material, did the AFM after exposing in air for few hours, and we see the AFM, the smoothness of the AFM pattern. From that, we confirm that this material is very air stable. And at this moment, we are trying to do more low dimensional device fabrication measurements. Anyways, so this material is interesting from the magnetism point of view also because if you look at the magnetism up to 400 Kelvin, it shows non-Curie-wise behavior, which actually made us think that it might be that this material might be a high temperature magnet, and the transition point might be even higher than room temperature, which is also supported by the moment versus field curve, which is also non-linear in nature. So from theoretically at least, we try to play with different spin configuration and see which one gives us the lowest ground state energy. And we actually propose that this material has a canted antiferromagnetic ordering, but still we are doing the neutron diffraction measurement to confirm whether this material has this particular spin arrangement or not. But this material is metallic in nature. It shows quantum oscillation, fairly high mobilities, which are very interesting. And theoretically, we also confirm that even at low dimensional and monolayer limit, this still remains metallic. And to be specific, metallic monolayers, finding a van der Waals system which remains metallic down to the monolayer limit is very rare. So there are very few candidates in this having this kind of properties. So we also use this idea to find some other exfoliable materials which are non-van der Waals. I'm not going to discuss the details, but here also we find a even a non-van der Waals system which we can exfoliate down to thin flakes. And this material, although having a 3D crystal structure, relatively more 3D, it has a lower quasi two-dimensional nature of both magnetism and electronic states. So even using this kind of symmetry arguments, we can actually find this kind of materials which are low dimensional, both low dimensional and non-van der Waals material, which can be exfoliated to low dimensional limit and then can be used for device fabrication. So it also shows very high mobility, which is expected, also anisotropic anomalous Hall effects. But just to leave you here, just so this is the one structural motif I talk about. But can we use this structural motif for even complex device fabrication? For example, Moore physics, which is a new frontier in low-dimensional materials research. So we know that if you have this kind of, let's say, you can create this kind of device, low dimensional device, you have higher degree of tunability, and create this kind of Moore patterns. Now, Moore patterns is very common in graphene because of the very simple hexagonal symmetry, and you can create different Moore patterns at small angles. But it's not only limited to graphene. Actually, recently with our collaborators, Professor Samsung Wu, at Princeton Physics, we showed that that even complex van der Waals systems like WT, which is like van der Waals topological semi-metal, we can create interesting Moore patterns and create this particular physics which observe this something called the 1D Luttinger liquid state. Anyways, so it is also gave us an idea, at least simulation-wise, can we get this kind of interesting Moore patterns even with squareness, and it's actually possible. So you can have this similar to graphene, you can have different kind of stacking with squarenet also. So even with tantalum cobalt telluride, which there are also now reports there are topological bands here. Just to like summarize, so this simple squareness motif is not so simple because it has lots of interesting physics involved, and you can have highly tunable systems, charges wave, magnetism, topological states, as well as high mobility carriers and van der Waals system in this simple motif. And just to lastly, so this idea is not only limited to square-net motif itself. You can have other structural motif, and from that symmetry, you can find interesting electronic states. For example, this is one project we recently started working on. Is that if you have a 1D linear chains in the 3D crystal structure, and if you have a strong enough spin orbit coupling in the between these chains, in these chains, you can actually create some this kind of localized state and something called flat bands. Now, if you are familiar with flat bands physics, now this becomes one of the most hot topic in condensed matter physics in low dimensional systems because of observation of flat bands in twisted bilayer graphene when you have kind of this strong correlation and then create superconductivity, ferroelectricity, and other properties from the flat bands. And also now this flat bands catalog.